the test you have coming up on from calculus. The important part that will be asked in that test will be the various types of methods of differentiation. So make sure that you are clear with applications of all the formulae like differentiation of x to the power n, then differentiation of trigonometric functions, sine, cos, tan, etc., logarithmic function, exponential function, etc. And then you are familiar with all the various techniques and properties of differentiation like product rule, quotient rule, and in particular chain rule. So that is the most important part of the revision from calculus that you have to do before the test, and also some basic type of questions related to application of differentiation as a rate measurer, like the area and volume type of questions that we've done from exercise 3, the first 2 or 3 problems, and also the type of problems in worksheets 1, 2, and 3. So this is the portion that you have to prepare for the test coming up. Now we have gone beyond that portion last time, and we have started with the discussion about the behavior of functions in terms of whether a function is increasing or decreasing from the value of its derivative at a point, whether it is positive or negative. So we will do a recap of that concept and start with some application examples of that. But as I told you, please keep in mind that your portion for the upcoming test will only be up to chain rule and its applications. It will not have behavior of the function and increasing and decreasing nature of the function as part of that.
So,
okay, Bhavika, I will discuss worksheet 1. You had a couple of doubts. Okay, we'll discuss that also. Okay, at some stage.
So,
yes.
So can you explain the steps to differentiate a composite function which has 4 to 5 embedded functions within it using chain?
4 to 5 embedded functions is going to be too lengthy for basic calculus level. It will not be really required. At the maximum, you'll have 2 embedded functions. Okay, so we'll discuss some examples. In fact, in worksheet 4, you have Ajay, you have a couple of doubts in that, Bhavika. Okay, in worksheet 4, in the first part, you have some first question. Some of the parts have couple of embedded functions. So those type of things are within the scope of this. Okay.
Okay, so can you discuss like
yes, we'll discuss that. Okay, 4 to 5, would be like, suppose I have log of sine of x square or x to the power something. So that kind of complexity in functions is not really required for our physics type of applications. But yes, embedded function within an embedded function, that's definitely part of the scope. Okay, so we'll discuss those examples also. Okay, so as I was saying, let's start with a quick recap of the last concept we saw in the lecture number 5, which is the behavior of the function from the value of its derivative. So we saw that we can understand whether a function is increasing or decreasing in nature in a given interval of x, okay, by understanding whether the derivative is positive or negative, okay, within subintervals. So behavior of a given function from analysis of its derivative. So the basic idea here is that we can understand this visually, that in the graph of a function, if the behavior or the nature of the function is such that it is increasing for a certain interval of x, then in that interval, if we draw a tangent at any point, it will have a positive slope by definition. Like for example, if this is the graph of the function y is equal to fx, now you can see that between this point A, let's say, and this point B, where the function sort of peaks, and then again after B it starts to drop. Then again, as it drops, it reaches the lowest point at C, and then again it starts to peak, and let's say goes up to T. So now you can see that if we draw a tangent at any point between A and B, like a point over here, we'll have a slope which is positive. And that correlates to the fact that if we move from one value of x to another value of x going along the positive x direction, we can see y is also increasing correspondingly in the positive direction. Same thing is happening for any point between C and D. If we draw tangent at any such point, again it will have a slope which is positive. But between B and C, you can see the function has the opposite behavior. That as x is increasing, y is tending to decrease between B and C. So if we draw a tangent at any point like this, you can see it's a straight line having negative slope. And we know that slope of tangent is nothing but the value of the derivative. So therefore, we have this analysis now that if dy by dx or derivative of the function is greater than 0 for a certain interval, let's say a to b, then it automatically implies that the function or the value of y increases with respect to the value of x for that same interval. Now, in the example graph that I've shown you, this applies to this interval or even to this interval, C to D. So again, this also applies to C to D. Whereas on the other hand, if the derivative of the function dy by dx is less than 0 for another interval, like in the example I've shown you, it is between B and C, then automatically it implies that y is decreasing with respect to x. For that same interval, B to C. Okay, so we will see this with some more numerical examples. Okay, but the logic of that should be very simple to understand. That derivative itself means rate of change. So if y is increasing, naturally the rate of change should be positive, and if y is decreasing, then naturally the rate of change should be negative. So if, for example, we have a function whose graph we are not aware of. Okay, so for example, let's say we have a function like this, 6x minus x square. So to begin with, we are not aware of the graph of this function, but can we use calculus to find out this behavior of the function? And yes, definitely we can use. All we have to do is we have to apply this concept over here for this particular function. So if we want to find out the intervals for which y increases or decreases with respect to x. So we can do that very easily by applying this concept over here. So in this example, you can see that expressed as a function, y is 6x minus x square. So the derivative of the function is differentiation of 6x minus x square. So that is 6 minus 2x. So now we can apply this to find out which interval or intervals in which y is increasing. And then we can apply this part here to find out which intervals x is decreasing in. So therefore, we can see that dy by dx is positive. That implies that 6 minus 2x should be greater than 0. That implies that 2 into 3 minus x should be greater than 0. Now, since 2 is a positive number, so obviously that means that 3 minus x should be greater than 0, or in other words, x should be less than 3. Or we can say that x belongs to the interval minus infinity to 3. Now, why I'll take the interval as minus infinity to 3? Because here you can see for the given function, there's no restriction on x. Y is defined for all real values of x. So the function is valid for x belonging to minus to plus infinity. But out of that entire interval, which part of the interval has dy by dx positive? It is up to 3. That means any value of x less than 3. So that means it's minus infinity to 3. Okay. So now finally what this tells us that y is increasing. I'll write this in short form with respect to x for the interval x belonging to minus infinity to 3. Okay. And there's no other interval, only this. Okay. Now similarly, if we are solving for dy by dx or derivative to be negative, so same thing, 6 minus 2x is less than 0. So 3 minus x should be less than 0 this time. So this will tell us that now x should be greater than 3, or in other words, x belongs to the interval 3 to infinity. So this tells us that y is decreasing with respect to x for x belonging to the interval 3 to infinity. So finally, these are the two things that we are looking for. And on the basis of this, we can understand that the behavior of the function could be, the graph of the function would be something like this. The value of x at which it reaches this point would be x equal to 3, because after that it's decreasing and before that it was increasing. So let's say this would be the x-axis. So this was how the behavior of the function can be understood on the basis of increasing and decreasing rate. Now also, of course, notice one thing here, that apart from all this, we can also see that at the point x equal to 3, the slope of the tangent is 0. So that's also evident over here, that exactly at the point x equal to 3, if I draw a tangent line, it will be a horizontal line. The slope will be 0. But I draw a tangent anywhere before that, it has a positive slope. I draw a tangent anywhere after that, it has a negative slope. So just go through this quickly and make a note of it if required. But so Bhavika, in this particular question, it was not necessary to plot the number line because there's only one factor, 3 minus x. But yes, we will see that when the inequality is more complicated, yes, then it is a convenient method. What you must have learned in maths is the wavy curve method or number line method. Okay. So we will see that that is applicable in certain cases. Okay, so hope this question is clear. Now let's oh sorry, that's not 8. Yeah, yeah. Okay. This is infinite. Yeah, thanks for pointing that out. Okay, so let's look at another example. So this time you try to solve this yourself. Okay. So now we have a slightly more interesting function, say x cube minus 3x. So again, we want to find the intervals in x for which the function increases or decreases. So apply the same method here, but just replace the function as x cube minus 3x instead of the quadratic function we had done earlier. So you see that here the inequality that you have to solve when you take dy by dx as greater than or less than 0 has more terms in it. It's a little more complicated. So you can use the number line method now, or the wavy curve method that you might have learned in maths. So just give this a try. I'll put up the solution in a bit of time. You can work out the question and send me a text with the answer. Okay, so very good. I have received correct answers from most of you. Akmal, your answer is correct. Heth, your answer is correct. Bhavika, very good, correct. Yash Sharma, correct. Kirti, your answer is correct, very good. So let's quickly work this out for the benefit of everybody. So we can see that dy by dx is 3x square minus 3, which we can factorize and write as 3 into x minus 1 into x plus 1 also. So now the condition for dy by dx to be positive is that 3 into x minus 1 into x plus 1 should be positive. So that means either both of these quantities should be negative, which means x is less than minus 1, or both of these should be positive, which means x is greater than 1. Or we can say that x belongs to the interval minus infinity to minus 1 union with the interval 1 to infinity. So another way of understanding this inequality is the number line method. So what we can do is we can visualize a number line for x like this. Okay. Now it's a product of these two things. 3 is a positive number. So let's start by visualizing x minus 1. So x minus 1 becomes 0 at the point 1. Okay. So 1 is the critical point for it, you can say. So for any value of x less than 1, x minus 1 has a negative value. And for any value greater than 1, it has a positive value. So this is how it looks like on the number line as far as negative and positive values are concerned. And the other factor is x plus 1. So for x plus 1, you can see the critical point is minus 1. So for any point where x is less than minus 1, x plus 1 is a negative quantity. And for any point or any value of x greater than minus 1, the quantity x plus 1 is positive. So now as far as the derivative is concerned, it depends on the product of these things. So x minus 1 into x plus 1, that you can see will be positive in this region, negative in this region, and again positive in this region. That's how we can say this. Okay, and similarly, so that implies that will be for x belonging to minus 1 to 1. Okay. Now notice that in the inequalities, we are not including the points 1 and minus 1 because at those points, the derivative is becoming 0. Additionally, dy by dx is equal to 0 at 2 points. Okay. So this function now has this kind of a behavior. Where this coordinate will be x equal to, this one's x coordinate will be x equal to minus 1. And this one's x coordinate will be x equal to plus 1. So you can see that the function y increases with respect to x for one to infinity, okay, and y decreases with respect to x for x belonging to the interval minus 1 to 1. Okay. So there are few examples of this type of question in question number 6 in your worksheet 4. So we'll discuss some of those examples as we go through that worksheet. But once again, I'm repeating that this analysis that we're doing today, the behavior of a function in terms of increasing or decreasing, this will not be asked in the test on Sunday. The test on Sunday is only up to worksheet 3 fully and question number 1 of worksheet 4. That is up to the concept of application of chain rule. And also simple applications of differentiation as a rate measurer.
So word problems given in worksheet 4 will also come, right? Like
Sorry,
similar.
can you speak a little louder, beta? I cannot hear you. Anirudh?
So word problems given in the question worksheet 4 can also come, right?
The question number 2, 3, and 4, those type of word problems.
Yes, sir.
The second one, yes, because it was a simple area type of problem, but the third and fourth are more complex. So those type of questions you don't have to prepare for the test on Sunday.
Okay, sir.
Okay.
Yes.
Okay, so now I'm switching over to worksheet 4. Okay. Acha, if in case anybody still has a doubt in any of the questions in worksheet 1, 2, or 3, please do let me know. We will, if required, discuss that also. Okay. Because that's a complete priority for your upcoming test. So anyhow, just give me a moment. I'm sharing the worksheet 4. Yeah, so let's start with question number 1 of worksheet 4. So quite a few parts, and all of them are basically applications of chain rule. So are there any questions we need to discuss in this? Anybody has a doubt?
So for question number 3, can you please confirm the answers for rate of change of tip of shadow, the position, rate of change of position.
Okay, okay. So question 3 is like the next one, right? Not, you're not talking about C over here, right?
No, sir, the word problem.
So
The
I'll come
shadow.
to that. Okay, I'll come to that. Let's go serially. Okay. Yeah, so so question number 1, Bhavika question part B. Okay, so let's start with this part B. So this is that type of question that we are talking about, that there is an embedded function within an embedded function. So it's like, from x, we first apply the quadratic function to get 1 plus x square. Okay. Then on that, we apply the square root function to get square root of 1 plus x square. And on that, then we are applying the exponential function to get e raised power square root of 1 plus x square. Okay. So it's like, we have to think of like a application of composite function concept of composite function within another function. So there'll be like two dummy variables instead of single dummy variable. Okay. So let's see this with the proper method first. So given this function, what we can do is we can substitute square root of 1 plus x square, let's say, as our first dummy variable z. So y becomes equal to e raised power z. But if you notice now, this z is also a composite function. So in this, further we substitute 1 plus x square as a new variable, let's say u. So z becomes square root of u. I'll write that here. Okay. So you can see u is related to x. Okay. Z is related to u, and e is related. Y is related to z. So now when we come to the chain rule substitution, we'll see. The chain rule step. We want to find out dy by dx, but we have written y in terms of what? Z. So that will be dy by dz. Okay. Then z is expressed in terms of u. So into dz by du. And finally, u is expressed in terms of x. So now differentiation of e raised power z with respect to e raised power z is e raised power z. Okay. differentiation of square root of u is 1 by 2 root u. Okay, and finally differentiation of u with respect to x is differentiation of 1 plus x square, which is 2x. So this becomes 2x e raised power z upon 2 times square root u. So even the 2 cancels out. Okay. And finally, we are left with what? This term x into e raised power z. Now z will have to resubstitute divided by square root of u. So that also we'll have to resubstitute. So we will now finally express this as dy by dx becomes x into e raised power z. Now z was how much? Square root of 1 plus x square divided by square root of u. Now u itself was how much? 1 plus x square. So this becomes our final answer. Okay. So yes, we can shorten some of the steps here because the first function is quite easy, but the proper way of solving it with all the steps shown and all that is going to be this. The proper way of showing the chain rule application is going to be through all these steps. Okay, Bhavika, so you've got this now, understood? Okay.
Yes, sir.
Very good. Now I can also simplify this a little because after all it's based on the exponential function. So I can quickly use this kind of trick that on the other hand, whenever we have a composite function which is based on exponential function, when we have any type of thing like this, that y is equal to e raised power f of x. Okay. So the general method is that dy by dx becomes e raised power fx multiplied by f prime x. Okay. So how we get this general formula? Because we know that we can substitute and write this as. Okay. So by using chain rule, so we can like skip this step, this first step that I'm writing below here. We can write this step directly as this. Okay. So when we do that, we notice that for this function, e raised power fx. So fx is what now? It is square root of 1 plus x square. Okay. So derivative of fx will become like, so you take 1 plus x square as z. So fx becomes square root of z. So differentiation of this fx becomes this. Okay. So now you substitute that directly over. So dy by dx becomes e raised power square root 1 plus x square into differentiation of that square root function. So that is x upon root 1 plus x square. So this simplifies it a little bit. But you understood now. Okay, good. All right. So any other doubt in the first question? Any other part? Okay, so let's move on to the next page. Okay, question 2, anybody has a doubt? E subpart, okay. Okay. Let's go back to question 1. Yeah. E subpart, now what we'll have to typically do is we'll have to separate these two out. So we can do a couple of things. One is we can use property of log. Okay, this you're familiar with, right? So let's use this. So that further means that y is equal to ln 1 minus x. Now you use substitution. So 1 minus x square is z, y is ln z. This can be a final answer. So this is a very easy way of doing it. Now there's another option also, we'll discuss that. Okay, so alternatively, what we can also do is, when we've expressed y as ln 1 plus x plus ln of 1 minus x, we can substitute this as, let's say, z1 and this as z2. So then y becomes ln z1 plus ln z2. So dy by dx becomes so this is this. Okay, so this is 1 by z1 into, now z1 was 1 plus x, so its derivative is 1, plus this is 1 by z2, but into z2 was 1 minus x, so its derivative is 1 minus 1. So this becomes 1 by z1 minus 1 by z2. That is 1 upon 1 plus x minus 1 upon 1 minus x. Okay. And when you solve that, you will get the same thing as this. Okay. So this method is clear. Yeah, Bhavika, I'll come to your question also. Okay, very good. Now, aside from this worksheet, let's say, suppose we have something like this, y is equal to e raised power 2x. So there are a couple of ways of understanding this. Okay, one is that we can take 2x as z. So y is equal to e raised power z. So dy by dx will become, so e raised power z into 2. That is 2 e raised power 2x. So you can see that on x, you have first operated this function, and then you operated the exponential function. So you're treating it like a composite function. Another way of doing this is that e raised power 2x can be written as e raised power x plus x. So that is e raised power x multiplied by e raised power x. You can also use product rule. First function into derivative of second plus second function into derivative of first. So e raised power x into e raised power x plus e raised power x into e raised power x. You can use this also, but it's really unnecessary to do this. Now this is like, we can do it, there's no problem, but it's really not necessary. Okay. So this is the easier way to understand.
Okay, sir.
So so likewise, like not only exponential function, but for example, if we have something like this, y is equal to sine of 5x, okay, then what is dy by dx? It is going to be 5 cos 5x. It's not going to be cos 5x, because again same thing, from x we have operated this linear function first, so we got 5x, and on that we've operated the sine function, so we got sine 5x. Of course, there are many other ways by which you can do this also, but they are completely unnecessary. Like if I really wanted to complicate matters, I could write this as sine of, for example, 3x plus 2x. Okay, totally unnecessary, but I can do that. Then differentiate this whole thing, use product rule here, use product rule here. But why to do something like that? It's totally unnecessary. Just by using chain rule concept, you can get this directly. Okay, so moving on, let's come to these questions. So yeah, let's discuss second question also. So if you notice in the second question, what's happening? We are having a disc kind of thing, thin sheet which is circular, so it's a disc of ice. Okay, thin disc. Now it's given, the rate of change of area is given to us. Okay, and the area at a certain instant of time is given to us, and what we have to find is the rate of change of the radius at that point of time. So what one way we could do this is, let's find radius as a function of area. Okay, and then let's apply the chain rule. So that will be derivative of this function into dA by dt. That's one way we could do it. Or another way we could do it is that we know area is a function of r. So dA by dt is the derivative of that function into dr by dt. So this is the unknown quantity, this is the known quantity. This also we'll have to substitute. Okay. Now I'll tell you why the first approach is easier. When we do it by the first approach, you will see it's going to be faster in number of steps compared to the second one. So if I go with the first approach, I know area in general is pi r square, this question. So I can reverse this and say that, okay, radius is equal to square root of a by pi, or in very simple terms, that is 1 upon root pi, which is a constant, into a to the power half. So this is the relationship between radius and area. Okay, so this is radius as a function of area. Okay, so dr by dt should be differentiation of this function. So that root pi is just a constant. Now we can use chain rule here. So further that will become 1 upon root pi into 1 by 2 root a, okay, multiplied with dA by dt. So this is our dr by dt. So this is the relationship that we are getting between dr by dt and dA by dt. Now we can just substitute the information given, that the area is decreasing at this rate. So dA by dt should be written as minus of 0.5 meter square per second. Okay. And at that instant, when the area of the sheet is equal to 12 meters square, so at that instant we have to find dr by dt. So substitute that information here. So dr by dt at that instant will be 1 by root pi into 1 by 2 times square root of a, and a was 12 meters square, okay, into dA by dt, which is minus 0.5 meter square per second. Okay, so this will give us minus 1 by 4 into square root of 12 pi meter per second, or we can write this as this will become our rate of change of radius. Okay, so this is the direct straightforward way of doing this question. Okay. dA by dt was the known quantity, whereas dr by dt was the unknown quantity. So I expressed r in terms of a rather than a in terms of r. I expressed r in terms of a, so that when I differentiate, the left hand side is the unknown quantity for me, dr by dt. So just note this down if required. Then we'll also understand it by the other method where we directly use the function a is equal to pi r square. Instead of r is equal to square root of a by pi, we'll use the direct relationship that area is equal to pi r square, differentiate that and find the unknown quantity. Okay, people, let's look at the other approach. Okay. So the other approach for this is you let this function be this way only, pi r square, and differentiate this now. And use chain rule here. So that is differentiation of pi r square with respect to r into dr by dt. So this will give you this relation, dA by dt is 2 pi r into dr by dt. The thing is, now this is the unknown, this is the given quantity. So the unknown quantity will have to express like this. And the question is, now we'll also have to substitute the instantaneous value of r. So when area is equal to 12 meters square, okay, so that means r is equal to square root of 12 by pi in meters. So dr by dt will become 1 upon 2 pi r. Now r is square root of 12 and square root of pi goes in the numerator. Into dA by dt. Now this is decreasing at this rate, so as usual dA by dt is minus of 0.5. This will become So that is our dr by dt. So you'll realize that there's no difference between this and what we've done earlier. It's just there we expressed r in terms of a and then use the chain rule. Here we had the original expression of a with respect to r, and we use that expression to find dr by dt from the value of dA by dt. So they're like, same thing, but slightly different approaches. Okay, does anybody have a doubt in the fourth question? Sorry, in the third question, we'll come to fourth.
Sir, I have a general doubt.
What better? Can you speak again, please?
Sir, I have a general doubt.
Yeah, tell me, Ayush. Sorry, Kirti. Yeah.
Sir, in the module, it is given that dy by dx of a raised to the power x is a raised to the power x into ln
Into
a.
ln a. Yeah, there's a method to prove that. I'll express. Okay. So, for example, if you put the value of a as e, then automatically it shows you it's e raised power x only, because ln of e is how much? 1.
Yes, sir, it's a constant.
But what about the situation where a is not equal to e, where a is some general value? So there's a way of proving that. I'll explain to you. Okay. So you have y is equal to a raised power e, where a is any real, sorry, a raised power x, where a is any real number. Okay. Now I want to find dy by dx. Okay. So what I will do here is that I will use the property of log. Natural log, or log that is of any term like this, is equal to n times ln a. Okay. So if I use that property here, I can get rid of the a raised power x and make it x times ln a. You understand? So on this equation, take log on both sides. So ln y is equal to ln of a raised power x, but take the natural log. Okay. So ln y will become x times ln a. Okay. Clear up to this step?
Yes, sir.
Okay. Now what we can do is either we can take exponential on both sides. Okay. Or what we can do is we can differentiate directly. So that's easier. So differentiation of ln y is equal to differentiation of x times ln a. Now for this, we will again use chain rule. Because see, we have ln of y, but we are differentiating with respect to x. So differentiation with respect to x can be written as differentiation with respect to y of ln y into dy by dx. Okay. And on the other side, it's very simple. Ln a is just a constant, so it comes out. So ln a into differentiation of x, that's 1. Okay. So this equation, now see what it becomes. Left hand side, differentiation of ln y with respect to y is 1 by y. Okay, so 1 by y into dy by dx. Right hand side is how much? Ln a. Because differentiation of x is 1. So dy by dx is becoming how much? It is becoming y into ln a. And what was y to begin with? It was a raised power x. So dy by dx is becoming e raised power x into ln a. So that is how this formula comes.
Okay, sir.
So for example, if I have y is equal to 10 raised power x, and I want to find dy by dx at x equal to 0, let's say. So dy by dx becomes 10 raised power x ln 10. So at x equal to 0, this becomes 10 raised power 0, which is 1, into ln 10 only. Okay, now you will, I don't know if you're aware of this or not, but you'll study at some stage that ln of any number can be converted to log to the base 10 by this factor 2.303. Do you know this formula in maths?
No, sir.
Okay, so you learn this later. So you can convert anything from natural log to log to the base 10 by using this. So this further becomes 2.303 log 10 to the base 10. So that is just 2.303. So that's our answer. Okay. So this is just an example of the application of this. Okay. But at the same time, immediately in physics, we will not really require this function so much. We will more often we'll see that, like, in fact, in all our applications in physics, as far as exponential function is concerned, we'll be dealing with the direct e raised power x function and not some other number to the power x.
Okay, sir.
So, sir, but these logarithmic rules haven't been taught to us in maths yet.
You learn in algebra, don't worry. So
Yes.
I'll just tell you the basic logarithmic principles that you should know. Okay. I think some of these you might be knowing from class 9, 10th also. Okay. So these are that, any base log of a into b is log of a plus log of b. Okay. Any base log of a divided by b is log of a minus log of b. And any base including exponential, a to the power n is equal to n times log. So this is one set of rules that you should know. Just like similarly, in terms of exponent, you should know this, that x to the power a into x to the power b is x to the power a plus b. X to the power a divided by x to the power b is x to the power a minus b. And x to the power a raised to the power b is x to the power ab. So again, these are some laws of indices that you should know.
So these three laws of logarithm should be enough for the test.
Sorry, these will?
These three logarithmic rules are enough for the major test.
No, they're not directly in your test, but for example, this question that we did earlier, log of 1 plus x plus log of kya tha, x minus 1 or 1 minus x, whatever it was, you can do it by direct differentiation. But if you know this property, then you can also do it like that. Okay.
Yes.
Or for example, we want to differentiate. There was this question, square root of 1 plus x square ke log ko differentiate karna tha. So you can express this as log of 1 plus x squared to the power half first. Okay. That is half log of 1 plus x squared. So now it's easier to differentiate because you only have to differentiate this part. Half is a constant.
Yes, sir.
So knowing these will obviously help you in solving differentiation problems, but directly questions will not come from these properties. Okay? Only in terms of differentiation.
Okay, sir.
So you can make a note of these properties that I've listed out over here. These are the properties for log. Logarithm properties. And these are the properties for indices. So whenever you learn them in maths in your algebra portion also, just recalling this from physics will also help you out. Okay, let's come to the third question. Anybody has a doubt in the third question, or should we move on to the fourth question directly?
So can you confirm the answer for the rate of change of the position of the tip of shadow?
Sorry, confirm the rate of change of.
Rate of change of position of the tip of shadow. The answer.
Okay, we can do that. Okay, but see, the question is not exactly asking that. The question is only asking whether it is moving towards or away from. So the answer for this part will be that it is moving towards. Okay. This is the tip of the shadow. Okay, so the tip is moving towards the person. This is the person. Okay, and the answer to this is also it's moving towards the wall. Okay, I'll confirm the answer for the rate also, but this is your wall. So the very easy way to understand this is just geometrically, that after some time, if the person has reached here, because he's traveling towards the wall, so the person has reached here, then at that point of time, the tip of the shadow is here. Okay. So what will happen is that the distance between the man and the shadow, that will also be decreasing. And the distance between the wall and the shadow, that will also be decreasing. So both are decreasing distances. Okay. So the tip is also moving towards the person, the tip is also moving towards the wall. So we could just do it by understanding similar triangles in this diagram or anything like that. You can see there are two pairs of similar triangles. One at the initial instant, which was drawn in the original diagram, okay, and one that I have drawn over that in red, which is the new diagram after some time. So if you compare the two sets of similar triangles, you'll see that the bases of both the sets of similar triangles have decreased, which means that the tip has moved towards the person also. The distance between the person and the tip of the shadow is also decreased. And the tip has moved towards the wall also, because the base of that larger triangle has also decreased.
Yes.
Now, if we want to calculate rate of change, so like we can add one question to this. Okay, we can find, for example, find the speed at which the tip of the shadow is moving. Given that the speed at which the person is moving is 0.5 meters per second. So for that, now we can use the rate of change or calculus concept. Okay, so let's discuss that next. So again, we'll be using similar triangle concept only for that also. Okay, so I'm just switching to my regular whiteboard for a moment. Okay. So let's say this is the wall with the lamp attached somewhere here. So the lamp is at this height, which is 5 meters or 5 feet or whatever from the ground. Now, initially, the person is, let's say, over here. This is 2 meters. And the person is moving towards the wall. So now in this diagram, you can see that the tip of the shadow, we can find out the position like this, that consider light coming from this lamp. Something like this. Okay, so this is like a beam of light which is reaching at this point. So like this, beams of light here are also reaching. So all this part is illuminated. But a beam of light here is getting blocked by you. A beam of light here is getting blocked by you. So again, this part is illuminated with light. This part is illuminated with light. But this part in between, this is the part which is dark. There's no light here. So this is the shadow. From this point to this point. Let's say I take the person as EB. Take this point as C. And I take the position of the lamp as E and the base on the floor as B. So you can see that EC over here is the length of the shadow. So let's take that as x1 because that's a variable quantity. So we are taking this distance here as x1. And you can see that ED is the distance of the person from the wall. So let's take that as x2. So this is x2. So now I can also define this whole distance as, let's say, S. That is the distance of the tip of the shadow from the wall. So S is basically the distance DC. So this S in my diagram is x1 plus x2, and that equals to the distance of the tip of the shadow from the wall. This is where the tip of the shadow is. So these are the instantaneous quantities. Now you can understand here that x2 is decreasing with respect to time because the person is moving towards the wall. Okay. So in fact, we can say that dx2 by dt, the rate at which x2 is decreasing, is minus 2. The first thing we can understand. Okay. So therefore now x1 will also be decreasing, but we want to find dx1 by dt, how much that is. That is the rate at which the shadow length will be decreasing. And accordingly, we'll see that S is also decreasing. So we want to find out ds by dt. That will be the speed of the tip of the shadow. Okay. Because this other point D is stationary. No? So the rate at which S is changing, that will be the speed of the tip of the shadow. That is the speed of the point C. So how we will do this? So for this, we need to find the relationship between x1 and x2. Because we need to find out x1. From that, we'll find out S, which is x1 plus x2. So that's where our similar triangles concept will come in. So if we look in the above diagram, triangles ABC, okay, and DEC are similar. They're similar right angle triangles. So base upon perpendicular should be equal to base upon perpendicular. So from this, we can get the relation that x1 into 1 by 2 minus 1 by 5 is equal to x2 by 5. Now 3 by 10 x1 is equal to 1 by 5 x2, which will tell us that x1 is equal to 2 by 3 of x2. This becomes the important equation. So we'll plug in this relation here. So we'll find this, okay, and we'll plug in the relation that S is equal to x1 plus x2. Plug this in here, and from that we'll find this. Okay, so just try this out now. All the information that you require is given on over here only. That V is 0.5 meters per second. The height of the person is 2 feet, whereas the height of the lamp from the ground is 5 feet. So that is how we got this relation here. The similar triangle relation. So you don't need any other information. It's all given over here. Now from that, you just find out this thing, the speed with which the tip of the shadow is moving, and also the rate at which the shadow length is decreasing. That is the rate at which x1 is decreasing with respect to time. And for the speed of the tip of the shadow, you have to find the rate at which S is changing with respect to time. S is x1 plus x2. So understood this now, how to work out this question?
Yes, sir. I actually got the answer, but I was not sure whether it was the length
so
or
now,
the whole.
okay, so I'll work it out now. You can match the question, right?
Yes, sir.
Yeah. Bhavika, what was given 10? AD? Yeah, AD was initially given as 10, but of course, over here we won't need the initial value of AD also. Okay. The important thing is AD is changing with time. So of course, initially at t equal to 0, x2 is equal to 10 liters. For example, at some general time t, x2 will become 10 minus 0.5 t. So we can use this also. So from that we can find out x1. Okay. And from that we can find out how x1 is changing with respect to time. Or we can directly use the ratio of x1 and x2 and use that to find out. Okay. So just quickly work this out numerically. I'll confirm the answers for you. Okay, so let's complete this problem. So you can see that if x1 is this much, okay, then dx1 by dt is 2/3 of dx2 by dt. So that is 2 by 3 of minus 0.5. So minus 0.33 meters per second. So what this equation, the information it gives us is now that AC, that length, decreases at the rate of 0.33 meters per second. So the shadow length, that decreases at this rate. Whereas now using this relation that S is equal to x1 plus x2, you can write this as so ds by dt the minus sign. So that means S decreases at 0.83 meters per second. That means the tip moves towards the wall at the rate of 0.83 meters per second. So this is the full interpretation of this question. Hope this is clear to all of you.
Yes, sir.
Okay, now let's come to the fourth question. So this type of question, we have done an example in class last time. Only here the numerical values have to be fitted accordingly, according to the data which is given. So this speed is given to us as 15 feet per second. Now this is a quantity which is decreasing. So let's write it as a variable. Okay. Whereas because this person we are assuming is stationary, so the distance of the person from this point over here is a fixed distance. So let's take it as d. So d is a constant, okay, whereas x and theta, both of these are variables. Now you can understand from here that dx by dt is minus of b. So from this now we want to find d theta by dt. So it's an application of chain rule. Now we can see the easiest way to relate them is that tan theta is equal to x by d. So rate of change of tan theta is equal to rate of change of x by d. Now here I'll have to use chain rule. So d by dt of tan theta is d by d theta of tan theta into d theta by dt. This is my chain rule step. On the other side, capital D is a constant, so I can just bring it out and write it as dx by dt. So sec square theta is the differentiation of tan theta with respect to theta. So sec square theta into d theta by dt should be equal to 1 by d into dx by dt. Okay, so if I invert this relation, now I can say that d theta by dt is equal to 1 by sec square theta, which is the same thing as cos square theta by d into dx by dt. So this is the relationship between the two rate of changes, the rate at which x is changing and the rate at which theta is changing. Now we'll see how we have to substitute the values given over here, because it is given to us that at the instant when v is 15 feet per second, the value of x is 200 feet, whereas the value of d is 500 feet. So we'll see how we'll make use of that also. Okay, so now once we have got this relationship that d theta by dt is equal to cos square theta divided by d into dx by dt. Now you can see here that dx by dt should be replaced with minus v, where v is of course 15 feet per second. And now we want to find out d theta by dt at an instant when x is equal to 200 feet. Capital D is of course 500 feet. So at that instant when x is 200 feet, what is happening is this distance is s. So s is equal to 100 root 29. So cos theta is d by s. So it is 5 by square root of 29. So we have to use this value of cos theta, and we have to use this value of x over here, or rather this value of dx by dt. Okay. So further, so at this particular instant, what will happen? The value of d theta by dt, the rate of change of angle, will become cos theta at that moment, which is 5 by root 29 squared. So that is 25 by 29 divided by capital D, which is a constant 500, into dx by dt, which is minus 15. Okay, now this is in feet per second, this is in feet in the denominator. So you will see we'll get it d theta by dt in per second. Okay, so when we solve this, we'll get this as 15 into 25 divided by 29 into 500. So when you work that out, it will come out to be 3, but with the minus sign, minus 3 by 116. Now the unit is per second, feet and feet are cancelled. So when we express an angle in the SI unit, it is the dimensionless or unitless quantity of radian. So rate of change of angle per unit time in per second is equivalent to rate of change of angle in radians per second. Because 1 radian is basically just 1. It is the ratio of arc upon radius when the arc is equal to the radius. So 1 radian is just the numerical one, is just the number 1 without any unit. So 1, if d theta by dt is 1 per second, it's equivalent to 1 radians per second. So if it is x per second, it's equivalent to x radians per second. Hence, the unit of the rate of change of angle here will be in radians per second when we calculate it this way. So we had to find the numerical value of cos square theta to substitute in that equation. So how we did that is by using Pythagoras theorem and trigonometry for that triangle. So from Pythagoras theorem, we worked out the hypotenuse, and from the hypotenuse, we worked out the ratio of base by hypotenuse, which is the instantaneous value of cos theta at the moment when x is equal to 200 feet. Okay, so people hope the method of calculation, everything is clear here. Okay, let's come to question 6. So you have to apply this concept in question 6, the one we revised today, that if the derivative of a function is positive in a region, then the function is increasing in that same region. If it is negative in some region, then the function is decreasing in that region. So any particular questions you have doubts in out of question number 6, any of the parts? Again, I've skipped out by mistake from question 4 to question 6. So just, even though it's the 5th question in the paper, just treat it like question number 6. Okay, so let's start with question part C. So in this function, even before you start with the rate of change and all that, you have to understand one thing, that this is a function defined for all values of x other than 0. So x here should not take the value 0, because division by 0 is an illegal operation in maths. Okay? So y cannot be defined when we take the value of x as 0. So you can say that x is only this way. It is minus infinity to 0, union with 0 to infinity. So it is a set of all negative and all positive real numbers, but excluding the number 0. So now to find out why increasing or decreasing, y increases for dy by dx being greater than 0. So what is dy by dx? It is 1 minus 1 by x square. So for this, we did not use the number line. We can just see that so x square is greater than 1 means that x is greater than 1 or less than minus 1. Or we can say x belongs to the interval minus infinity to minus 1 union with 1 to infinity. So this is the interval for which y increases. Similarly, we'll find the interval for which y decreases. But only when expressing that interval in which y decreases, we have to be a little bit extra careful, because remember this condition over here. For this function, we should not include the point x equal to 0. The function is not defined for the point x equal to 0. Yes, we'll come to that, Bhavika. Okay, similarly, for y to be decreasing with respect to x, that means derivative is negative. So remember, we can't include the point 0 here. So this will be you have to write it like this. So it's minus 1 to 1, but excluding the point x equal to 0, because at x equal to 0, we can't define y. Okay, now in this exercise, gradually, as you move down, the complexity level increases, especially for the trigonometric function. So let's take the example of this one next. So that function was sin x minus cos x, right? For the interval x being from 0 to 2 pi. You want to find the intervals in which y increases or decreases with respect to x. So that was the question here. So as usual, we start by understanding the derivative of the function. So this implies so this is clear so far, I hope. Differentiation is equal to differentiation of sign, which is cos, minus differentiation of cos, which is minus of minus sign. So it will become plus sign. Right. Now I want to find the condition that y increases for dy by dx being greater than 0, or cos x plus sin x being greater than 0. So in other words, I can also say that cos x should be greater than minus sin x. Now from this, how I'll find the values of x? Let's understand that. Okay. So this is where a little bit of graph theory for cos and sin will help us. Okay. We look at the basic graph of for example, cos x. We can see that graph is like this. Now in that same thing, if we were to look at the graph of sin x, that looks like this. Okay. But interestingly, see, we are comparing cos x with minus sin x. So let's convert this to minus sin x graph. So how will the minus sin x graph look? Just take the mirror image of this. This is the graph of y equal to minus sin x. It goes to minus 1 at pi by 2. Okay. And then it goes to plus 1 at 3 pi by 2. Now, basically, I want to compare that when this graph, that is cos x, is greater than this red colored one, which is minus sin x. So let me superimpose the two graphs in the same diagram. So I want to solve for the condition that cos x is greater than minus sin x. So I'll compare the two graphs of the functions y equal to cos x and y equal to minus sin x to get the clarity on that. Okay. So cos x was the graph that was looking like this. Okay. Now in comparison to that, how did the graph of minus sin x look like? Minus sin x was a graph like this. So now comparing the two graphs, you can see that whatever this value is here, in this region, what is happening? Cos x is greater than sin x or greater than minus sin x. And then another region where that is happening is here. In this region, again, cos x is greater than minus sin x. Whereas in this entire region in between, you can see in this region what is happening. Cos x is actually less than minus sin x. So now all we have to do is we have to find this point where cos x is equal to minus sin x. So that is which point? Over here, this will be 3 pi by 4. And over here, this will be 7 pi by 4. And this value is minus 1 by root 2. This value is plus 1 by root 2. Okay. So if we looked at dy by dx, which was cos x plus sin x earlier, you can see that for x belonging to the interval 0 to 3 pi by 4, what is happening is that cos x is greater than minus sin x. Therefore, why is it? Okay. But similarly, in the next interval which I've drawn in the graph, for x going from 3 pi by 4 to 7 pi by 4, this entire region. And finally, so you can see here that y increases for these two intervals, 0 to 3 pi by 4 union with 7 pi by 4 to 2 pi. Or we can write this as 0 to 135 degrees union with one loop. So bit of a complicated question when it comes to the analysis of whether dy by dx is positive or negative and the solution of that inequality. Okay, so just note down this method. We will do more practice and we gain more insights into questions like this over the next couple of lectures. Okay. But as of now, you have to solve it by this kind of analysis here. Yeah, Bhavika, we can take random values and all that, but it's not going to be easy, no? You understand the point, not? Taking random values and checking is not going to be very easy over here, because you know, how will you know the exact values at which the behavior changes from going from positive to negative and vice versa? No?
Okay, sir.
Now, for example, another case of this kind of analysis which I had given you to solve. No, I don't think I've solved the first question of the assignment wrong. You mean question number 1, part A? No, I've not solved it. Do you have a doubt in that question, beta? Okay, I'll explain that to you. Okay. So y is equal to square root of 1 plus sine square x. You have to find dy by dx. So first step, substitute. To take 1 plus sine square x as z. So y becomes root z. Okay, so then chain rule. So now you can see from this dy by dz will be just differentiation of square root of z or z to the power half. So that is 1 by 2 root z. Okay, so this step is coming as 1 by 2 root z. But what about this? So for differentiation of this, again we have to use chain rule. Okay. Z is equal to 1 plus sine square x. So for dz by dx, again use chain rule. Take sine x as some new variable, let's say u. So therefore, z becomes 1 plus u square. So it's like that embedded composite function, one composite function inside another. Because from x, we have first operated sine function. So we got sine x. Then on that, we have operated the 1 plus square quadratic function. So we got 1 plus sine square x. And then on that, I've operated the square root function. So I've got square root of 1 plus sine square x. So there will be two dummy variables involved like this. So now dz by dx is equal to dz by du, so into du by dx. Okay. So that is so 2u into cos x, and u itself is what it is, sin x. So this is our dz by dx. So this is what we'll now substitute. So z was 1 plus sine square x. Okay, so this 2 also cancels. Square root of z. So this type of question, you have to have plenty of patience while you're solving, because there's two layers of substitution you have to do. First, I have substituted 1 plus sine square x as z. So I'm getting y as a function of z. And then in that, I've substituted sin x as u. So I'm getting z as 1 plus u square. So it's the use of that chain rule step or that composite function concept twice. Okay, people. So hope this is clear. So the last few questions of question number 6, I mean the last few parts of question number 6, you can try them out, but I would suggest try them out after your test on Sunday. You try it out on Monday or Tuesday. We'll discuss them as more examples in the next class. But for Sunday's test, you will not have this concept of increasing or decreasing nature of the function. So the inequality part is not important, okay, for this test, that is. So just make sure that you are very thorough with the chain rule applications. So the first question of exercise 4 or worksheet 4's question number 1 gives you good practice in application of chain rule. So make sure you do that properly. And at least question 2 and 3 of the rate of change concept or the application of derivative as a rate change calculator. Make sure you go through that section also properly. And before that, worksheet 1, 2, and 3 and the questions which I've given you specifically from the exercises earlier, make sure you practice out those questions. Also, if you do a revision of the content that we've done in class, especially up to lecture number 5, that is last time, that should give you a very good platform to score marks from in the upcoming test, right? Yes, today I will give you a new assignment, but that will be like a revision assignment. So that will help you with the revision for the upcoming test. Yes, Bhavika, I'll explain to you next time how the usage of critical points can help us in analyzing those kind of problems where the function is increasing or decreasing.
So in the first worksheet which you gave us, in that we never used dy by dx anywhere.
In which one? The
First worksheet.
Yeah, in the first worksheet too, we just had seen the basics of rate of change concept, no?
Yes, sir.
But now that you know dy by dx concept or instantaneous rate of change using differentiation, you can also interpret those questions in terms of differentiation. No?
Yes, sir.
There we had interpreted instantaneous rate of change in terms of delta y by delta x only, but delta x tending to 0 or very small, you know?
Yes, sir.
So now you can equate that with dy by dx and understand it from differentiation concepts also. But it's anyway going to be very easy, those kind of things, right? Okay, so Bhavika, I don't know, maybe if you something in your settings or probably your issue with your microphone, you're not able to unmute, but you have any other question, you can ask me through the text message also. Okay. Oh, for the test 1, just revise questions from worksheet 1, 2, and 3, Bhavika. Okay. Worksheet 1, 2, and 3, and question number 1 of worksheet 4. Okay. 1, all the parts. The chain rule application questions. Okay. And apart from that, some specific questions I had asked you to do from your module exercises, which we had discussed in lecture number 4, I think. Okay. There were 3 questions from exercise 3 and a few questions from exercise 1 and 2. So those questions, make sure you revise once more. And also the lecture notes. Okay. So you can try out doing all the questions we have done in class. You can do them again on pen and paper yourself and see if you are comfortable with all the steps and all that. In case of any doubt, you can always send a particular question to me by WhatsApp or the doubts page, and I'll help you out with that before the test. Okay, so I think with this, you should not have any difficulty with the test coming up on Sunday. Okay, make sure you're doing the same for vectors also, according to the syllabus of vectors. You should be good with physics. That's it for today, people. Wish you all the best. Thanks for attending.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Okay, people. Bye.
Sir,
Yes.
sir, can you send the answer key of the revision paper which you will send today before Saturday or
Yes,
on
yes.
Saturday?
I will send the answer key sooner than later.
So, thank you, sir.
Okay.
Thank you, sir.
Okay.
Thank you, sir.